Everybody, welcome back to chemistry. And so now what I want to talk about is something called resonance in Lewis structures. So let me talk a little bit about what resonance is. So oftentimes you will be writing a Lewis structure for a molecule. And what you'll find is that maybe you can write more than one Lewis structure. And both of these structures, or more than the two of these structures, are correct Lewis structures that you have written. So what resonance is sort of understanding the relationship between the multiple, alternate, and correct Lewis structures that you have written. So what I want to first do is sort of give you an example of a case of a molecule where you can write a couple of good Lewis structures for that, and we'll talk about how resonance between the Lewis structures is involved. So the first thing I want to do is, the example I want to use is a molecule called ozone. So ozone has a formula of O3. So this is ozone. So you may know that in the atmosphere we have mostly diatomic oxygen, which is O2, but at the upper layers of the atmosphere we have another different kind of molecule of oxygen, whereas you have three oxygen atoms bound, and this is called ozone. And so what I want to do now is write out the Lewis structure for ozone. So let's just do this sort of in the standard way and see where we go. So you know that oxygen has 6 valence electrons, and it looks like we have 3 oxygen atoms that we have to deal with, and so we will have a total of 18 valence electrons that we have to put in the Lewis structure. So that would be 9 pairs that we have to place in the structure. So we have 3 oxygen atoms here. So for the moment, I'm just going to draw them in the line. So that's easy enough. So that is a good skeletal structure. So let's go ahead and throw in the 9 pairs. And so you know at this point that the first pair will go in to bind 2 atoms together. And same thing with the second pair. And then here's pair 3. We're going to put lone pairs on the outside atoms first. 4, 5, 6, 7, 8, and 9. Okay. So I think at this point what you can do is sort of evaluate whether these 3 oxygen atoms have octets. And so what you can see is that the oxygen atom on the left will have an octet of electrons. The oxygen atom on the right has an octet of electrons, but the oxygen atom in the middle does not. It only has 6 electrons. And I think you know at this point what you can do about that. So what you can do to make sure that the middle oxygen atom has an octet is you can move this lone pair here, for example, on the left oxygen, and you can move that into the bond between the left oxygen and the middle oxygen. So let's go ahead and do that and see what we have. And so what we'll have is this, and now we have 2 pairs of electrons between the left oxygen and this middle oxygen. And so we'll finish the structure like that. So let's just take a look at this and decide whether this is a reasonably good Lewis structure. So in terms of octets, it looks like we're now good. So all atoms now have octets. So now let me go ahead and replace the shared pairs of electrons with lines. So this is what I have for the final Lewis structure of ozone, which is this. And so this looks like a perfectly good Lewis structure. Now, just for clarity, let me erase this and let me point out something to you. So the way we created this perfectly good Lewis structure is we moved this lone pair from the left oxygen to become a shared pair so that all oxygen atoms here would have an octet. But you don't necessarily have to move that lone pair from the left oxygen. You could have moved this lone pair from the right oxygen. So that's now what I'm going to do. So let's go ahead and move this pair from the right oxygen into the bond between the central oxygen atom and the right oxygen atom and see what we get. So this time I'm going to write this over here. So what we have now is this. So now we have two shared pairs of electrons between the middle oxygen and the right oxygen. So this looks good. And so it looks like all the oxygen atoms have octets. So I'll finish the Lewis structure by drawing lines for shared pairs so it will look like this. Okay. So let me focus our attention on these two Lewis structures by just kind of erasing the prior stuff that we have here. So I'm going to call this one here on the left a left Lewis structure, and I'll call this one on the right Lewis structure. So the first thing I want to kind of point out is, as far as I can tell, we have drawn these Lewis structures perfectly correctly, because in each case we have ensured that all the atoms in the structure has an octet. So that is good. And so both of these Lewis structures are perfectly correct. But you can see that they're a little bit different from one another, in that here we have the oxygen on the left receiving the double bond from the middle oxygen, and here on the right we have the oxygen on the right receiving the double bond, the oxygen. So there may be an issue here, and what I'm going to do is sort of describe the issue by talking a little bit about what the true ozone molecule looks like. Okay, so what I'm going to do is draw a picture, as best as I can, of what a true ozone molecule looks like. And so ozone, if you were to look at its structure through some technique, like say electron diffraction, you would pretty much see its three oxygen atoms bound together. Now, one thing I'm doing to simplify this picture is I am not drawing that the terminal oxygen atoms are at an angle, which they are from the central atom. I'm kind of drawing them in the line. That'll be fine for now. So we have the oxygen atom in the middle, we have the oxygen atom on the left, and we have the oxygen atom on the right. Now, if you were to look at the true structure of ozone, what you would find is that the distance here between the oxygen nucleus in the middle and the oxygen nucleus on the left, we'll call it X, and the distance between the nucleus middle and the one on the right is the same distance, X. So what we hope is that our Lewis structure that we have drawn suggests that the bonds between the central oxygen atom on the left and the central oxygen atom on the right are identical. And we want them to be identical because apparently these left and right oxygen nuclei have the same distance from the central oxygen nuclei. So the question is, do these Lewis structures suggest that these bonds from the central oxygen atom to the left or the right oxygen atom, are they identical? And you can see in both structures the answer is no. So let me talk a little bit why these Lewis structures say that that is not true. So here on this left Lewis structure, we have a double bond to the left atom and we have a single bond to the right atom. Now, one of the things you're going to learn a few lessons from now is that when you have oxygen atoms or other atoms held together by a double bond, those atoms will be brought in closer than, say, if you had oxygen atoms or other atoms held by a single bond. So double bonds tend to be shorter than single bonds. So with this Lewis structure here on the left and the one on the right, what they're saying is that we might expect in the oxygen molecule that one of the distances between these two oxygen atoms, say the left and the middle there, will be shorter than the distance between the right oxygen atom and the middle one. But we know, again, in the true structure of ozone, that is not the case. So we have a problem here. We have written out two correct Lewis structures for ozone, but they don't really truly well represent the real structure of ozone. And so what we have to do is we have to think of a way that we can sort of represent, at least in our minds, a Lewis structure that most better represents the true structure of ozone. And so what we might do is we might merge the left and right structure together in our minds and think about what we get. So I'm going to merge the two structures here. I'm going to draw a picture of that here. So we have an oxygen in the left, oxygen on the center, and the oxygen on the right. So one thing you can see that they all have in common is that they at least have a single bond to both atoms. So here's a single bond and a single bond here. Now, what I want you to notice is let's merge the left bond to the left oxygen atom. Imagine what we get here. So in this left Lewis structure, we're looking at the left bond, we see a double bond. On the right Lewis structure, we're looking at this left bond, we see a single bond. So when we merge those together, we might expect that we would not have exactly a double bond or a single bond, but something in between. We would have a bond and a half. So to indicate that we have a bond and a half, I put a dashed line between those two oxygen atoms. You can do the same thing from the central atom to the right atom. You merge the single bond in the left structure with a double bond in the right structure. And so you would have a bond and a half. Now, this structure here, which I have written, is not formally a great Lewis structure because I'm leaving out lone pairs, which I'm allowed to do. But this structure really better represents the true structure of the molecule. So this structure, which best represents the true structure of the molecule, and may not be a perfect Lewis structure because you're maybe leaving out lone pairs in the structure and you're drawing partial bonds. This is something called a resonance hybrid. And so when you figure out what the structure of the resonance hybrid is, the goal is to make it as representative of the true molecule as possible, and we have done that. Now, how did we get this resonance hybrid structure? What we did is we merged two correct left and right Lewis structures here that were inaccurate, and we merged them in our mind to produce a more accurate resonance hybrid, which is closer to the true structure of ozone. So the two structures that you merge together, the correct Lewis structures, which are not really accurate, those structures are called resonance forms. So I'll write here resonance forms for ozone, O3. So we have two of them here. And again, these are two correct Lewis structures that are not exactly accurate. The way we sort of, as chemists, sort of describe that these are resonance forms is that we put the forms within brackets, and then what we do is we put a double-headed arrow between them. And the purpose of the double-headed arrow is to remind us, when we look at these two correct Lewis structures which are inaccurate, what we have to do in our mind is merge them together to produce what we think is a better picture of what the structure looks like, which is the resonance hybrid. Okay, so I have a slide that sort of describes that, which I want to kind of bring up. Let me see if I can bring that up here really quick. Okay, so let's take a look at this slide. Okay, so I think a really good way to think of an analogy for Lewis structures is to look at the example of dog breeding. And so I have a slide of that here. And so what you can sort of see on the left side is, for example, a picture of two breeds of dogs, a German Shepherd on the left, a Labrador Retriever on the right, that you mated as a dog breeder to produce the hybrid dog, which, for lack of a better phrase, I'm going to call it a mutt. Okay, so let's take a look at this mutt here. And so if you are the owner of this dog, this mutt, I mean, it's a real live dog, right? And you might describe it as saying, well, this dog has partly German Shepherd properties and Labrador Retriever properties. Now, this does not mean that the left half of the dog is a German Shepherd and the right half of the dog is a Labrador Retriever. You're just saying that these are the two breeds that sort of exist and that you kind of merged into this new dog, this mutt. And so the mutt, the final dog, which is alive and well, represents a sort of a mixture of the German Shepherd breed and the Labrador Retriever breed. And so we can sort of say the similar thing. Instead of looking at, say, a living mutt, let's look at a living molecule. And here the living molecule is ozone. So here is ozone molecule. And so that structure that is there that I've circled is the resonance hybrid. And you can see again, the resonance hybrid sort of indicates that the bonds to the two oxygens on the left and the right are similar in that they're both 1 1/2 bonds going to both oxygen atoms. And so that is the best, most correct structure of ozone. Now, how did we create that structure of ozone? What we did in our minds is we merged, if you will, two breeds or two correct resonance structures, the one on the left and the one on the right. So what we have to sort of do is when we look at that ozone molecule, we have to recognize that that sort of resonance hybrid there, that is the best structure, but it is comprised of other structures that we drew that were really sort of fabrications. The fabrications were not perfectly correct, but when we averaged in these fabrications, these Lewis structures, in our minds, then they are better representation of the true structure of the ozone molecule. Okay, so we're going to sort of move back to the glass board, and let me just give you one more quick example here. So the final example I want to go over here of a molecule which has resonance forms is the carbonate ion. So this is CO3 2-. And so let's work out really quickly how many valence electrons we're dealing with. So carbon has 4 valence electrons, oxygen has 6 valence electrons, and there are 3 of them, right? And then here, so from the oxygen, we should have a total of 18 valence electrons. And then carbonate is an anion, it has 2 extra electrons, so we have to account for that. So if there's 2-, there are 2 more electrons we add to the count. And so how many total electrons do we have here? It looks like we have 24 electrons we have to deal with in this structure, or 12 pairs. Okay, so let's go ahead and try to draw out a Lewis structure. So we have carbon in the middle, oxygen will evenly distribute around the carbon. The reason why carbon is in the middle and not the oxygen is because you might remember carbon is less electronegative, and you put the less electronegative element in the center of the molecule most of the time. So that's why I put it there instead of oxygen. Okay, so 24 pairs. So the first pair, I'm just going to make my life easy and draw it as a line. That's a shared pair. Second pair, third pair. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so now what you can probably see is that this is not really a good Lewis structure, and the reason is the carbon in the center does not have an octet. So what we can do, as you know, is we can move, say, this lone pair from the upper oxygen to go into the bond between that carbon and oxygen. So let me write out that structure. So it's carbon, it'll be double bonded to oxygen, and there are 2 lone pairs left on that oxygen. And then we have an oxygen here and an oxygen here. And these have remained the same. Now, so this is a good Lewis structure because all the atoms, carbons, and the 3 oxygens have octets. Now, the question is, can you write an alternative perfectly good Lewis structure? And the answer is yes. And so I think you sort of know what I'm probably going to do at this point. So what I'm going to do is I'm going to look here at this lower oxygen. Instead of moving the upper oxygen's lone pair into that bond, we'll look at the lower left oxygens and move its pair into that bond. So what I'll do is I'll draw an alternative Lewis structure that looks like this. And this is, again, a perfectly good Lewis structure, but it's not the same as the one I wrote previously, because now we have a double bond that's going to a different oxygen atom. And so this is a good structure. And so I'm going to do what I just did one more time, except here what I'm going to do is I am going to move this pair from the right oxygen into its bond. So let me write a final Lewis structure here. C-O, getting a little sloppy here. Okay, here we go. Double bond to this oxygen on the lower right, and then single bond to the oxygen on the lower left. Okay, so let's talk about these 3 structures that I made for carbonate. So you can see immediately they're all perfectly good Lewis structures, but guess what? What these Lewis structures might suggest is that the true carbonate molecule, it would have a carbon in the center and there would be 3 oxygen atoms bound to the carbon, but it might suggest that one of the oxygen atoms has or is a little closer to the carbon than the other oxygen atoms, because here these Lewis structures suggest that to one oxygen atom you have a double bond, and so in theory that should bring that oxygen atom closer to the carbon, and the other 2 are single bonded, so they may be a little further out. But as you might imagine, that is not the true structure for the carbonate anion. And so what it really looks like is you have carbon in the center, and then the oxygen atoms that surround it are equally distant from that central carbon. So the bonds between the carbon and those 3 oxygens should be the same length. So what we have to do then to get a really better idea of what the carbonate molecule looks like is we have to take these structures which I've written These are perfectly good Lewis structures, and we can say that these are resonance forms. So to do that, I'm going to put double-headed arrows between the structures and put brackets there. And we're going to merge these three structures in our mind and see what this looks like. And so what you can probably guess is you have a carbon here, you have an oxygen here, an oxygen here, an oxygen here. So let's figure out what the bonds between the oxygens will look like. And so our goal here in making a final structure is ensuring that each of the bonds to each of these oxygen atoms are basically the same, because that's what it's like in the real molecule. So what we might imagine here when we merge these three structures in our mind is that we're going to merge in one structure of a double bond here with one structure with a single bond and one structure with a single bond. And so what we might imagine that this bond from carbon to this oxygen, it has 1/3 double bond character and 2/3 single bond character. And so what we might imagine that this bond to this oxygen here is really 1 1/3 bonds. And so we can do the same things to the bonds to the other oxygen atoms here. And so this one is also 1 1/3 bond. And then this one also is 1 1/3 bond. And so what you can see is when we have merged these resonance forms of carbonate into our mind, we have created a final structure where the bonds between the carbon and the different oxygen atoms are identical. And so this is a better representation of this true structure of carbonate. You could put in lone pairs on the oxygen, but that can be kind of tricky because if you were to be rigorous about it, you want to make sure that the structure in the end has as many valence electrons as it should have. And that might be a little bit difficult to figure out exactly where you put the lone pairs on the oxygen atoms to ensure that that happens. So you can leave out the lone pairs again. So this would be the final structure for carbonate. And then this structure here is called a resonance hybrid. So let me point out one more thing. So again, we wrote out these resonance forms for the carbonate ion. Again, all these forms are perfectly good Lewis structures, but they're not really a good accurate representation of what the true carbonate molecule looks like. So we merge them together in our minds, and so this resonance hybrid is a better representation of what the true carbonate anion looks like. So thank you for listening to that. We will see you next time.